like to take your seats now? Okay, we're very fortunate today to have two eminent atmospheric chemists give seminars. Our next speaker, Professor Roger Atkinson, is a very well-known, internationally respected atmospheric chemist. He is the director of the State Air Pollution Research Center at UC Riverside, the co-author of over 300 peer-reviewed papers. He's received many awards, including the Distinguished Professor of Atmospheric Chemistry Award from UC Riverside. And he is an internationally recognized expert in the field of gas phase reactions of organic compounds and has contributed much to this field. Please join me in welcoming Professor Atkinson.
Thank you, Eileen. Okay. So I'm going to talk, the contract I'm talking about was completed, I don't know, a year ago nominally. Although some of the work I'm going to be talking about was done sort of post final report to complete up a few things. So we'll get going. We're talking about atmospheric chemistry of monocyclic and polycyclic aromatic hydrocarbons. As you all know, they're present in gasoline and diesel exhaust, or actually gasoline and diesel fuels and in their exhaust. The most abundant ones are benzene and the alkyl benzenes, which is benzene, toluene, the xylenes, ethylbenzene, and 1,2,4-trimethylbenzene, and Janet pointed out naphthalene and the C1 and C2 alkyl naphthalenes, and that's pretty well what I'm going to be dealing with. Transformation processes in the troposphere. All of these react with OH radicals during daytime, and they can react with NO3 radicals during nighttime and evening hours. And if you put the rate constants, reaction rate constants together with, or combine them with measured or estimated NO3 and OH concentrations, it's quite evident that the daytime OH radical reaction is expected to be the dominant loss process. And all I'm going to be talking about is OH radical reactions, so the daytime ones. These OH radical reactions proceed by mainly by OH addition to the aromatic rings at room temperature and below. At elevated temperatures, they can switch over to H-atom abstraction. So if you're dealing in combustion systems or combustion temperatures, it would be H-atom abstraction, but for atmospheric chemistry, it's mainly OH radical addition to the aromatic rings. And so for toluene, we have these potentially two processes. Well, there are two processes. This one, which is the H-atom abstraction, forming a benzyl radical. Room temperature, this is about 7% of the overall reaction. And then most of it forms this species down here, or an isomer. The OH can add at various places around the ring. There is, in fact, an equilibrium here, but it lies this way, and essentially, for atmospheric conditions, this is a stable species. It's not going to decompose backwards, but it does at elevated temperatures. And I'm going to call this, when I find my arrow, an OH-aromatic or an OH-PAH adduct, if I'm talking about PAHs. So the real key is what happens to these OH-PAH adducts. These things, this benzyl radical believes that it's essentially a substituted alkyl radical. It behaves just like a methyl radical or an ethyl radical. But the OH-aromatic adducts are a real problem area. About 15 years ago, the German group from mainly Cornelius Zech, showed that these OH-aromatic adducts react with both NO2 and O2 in the atmosphere. I measured the reaction rate constants, but what I work it down to is, if I can again find where my arrow has disappeared to, there it is. These OH-aromatic adducts reacting with O2 and NO2, these reactions are at equal importance in air at room temperature at about 1 part per million of NO2 for benzene, about 3.3 part per million for toluene, and somewhere around 10 parts per million of NO2 for the xylenes. So clearly, even in our worst days, don't really get up to a part per million of NO2. And so under ambient conditions, these OH monocyclic aromatics react with O2. But the observation in the atmosphere of nitro-PAHs, as Janet mentioned a few minutes ago, from the ones that are formed from gas phase OH radical initiated reactions, suggests that in the case of the PAHs, that the OH-PAH adducts must react to a significant extent with NO2 even under ambient conditions. And so we can sort of have a generalized reaction, which is the NO2 reaction gives products which can include nitro aromatics. The O2 reaction gives products which may in certain cases be the same, but they're mainly dicarbonyls. And we shouldn't forget that, as Janet mentioned, that the NO2 reactions can also give these ring cleavage dicarbonyls. But clearly, the nitro-aromatics have to come from an NO2-dependent pathway. Previous literature data or previous work both by us and some other groups has clearly shown that at least for the monocyclics, that there is this NO2 dependence in the products. This is some work we did about 6 or 7 years ago for paraxylene, looking at 3-hexene-2,5-dione, it's a ring-opened dicarbonyl as a function of NO2, and you can see that the yield drops off from about 30% yield at low NO2 down to around 20% at high NO2, and I point out that this is 1 part per million of NO2, wherever we are there. So in this case, the two reactions, the OH paraxylene adduct with O2 and NO2 are equal somewhere way over to the right, about 10 parts per million. And the other one, which is one portion we're going to be interested in this contract with the Resources Board, was to look at nitro-aromatic yields. And this was previous data, some data we'd done back in 1989, reanalyzed more recently. And this is 3-nitrotoluene, the yield of 3-nitrotoluene as a function of NO2. And you can see as the NO2 decreases, the yield decreases fairly rapidly, or slowly at first and then more rapidly, essentially linearly. Ambient at 250 parts per billion of NO2 is this little red square down here. And I point out that two things. This line drawn through it is in fact the literature data from Zetsch's group in Germany of the reaction rates for the OH-toluene adduct with O2 and NO2. The 92% of the reaction is known from product studies to go by addition to the aromatic ring. And the only fitting parameter was the yield was alpha, which is the yield of 3-nitrotoluene from the OH-toluene adduct reaction with NO2. And the other thing, and we'll come back to those numbers later on, the other thing is that these data are only extended down to about half a part per million of NO2, still well above anything in ambient, luckily. So the specific tasks we carried out for this project were to look at ring cleavage dicarbonyls from aromatics, monocyclic aromatics, to develop, and this was sort of part of our second, of number 3, was to develop a reliable and convenient in situ source of Glyoxal, which is one of these ring cleavage dicarbonyls for calibration of our analysis methods, and I'll just mention why that's sort of important. And then it was to look at ring cleavage dicarbonyls from OH plus a series of PAHs, and the last one, but certainly not the least, was to look at nitro-aromatic and nitro-PAH yields from the OH reactions as a function of NO2 going down to ambient levels to try and see just what the sort of yields would be under ambient conditions. So we'll start off with the first one, which is carbonyls from OH plus monocyclics. We did toluene, the xylenes, and the trimethylbenzenes. OH radicals were generated by the photolysis of methyl nitrite. It's a nice 3-step mechanism. We've used this for many, many years. Reactions were carried out in a 7,000-liter Teflon chamber with black lights. This picture has 20% of the black lights on, which is fairly typical conditions. We had initial concentrations of about a part per million of everything, i.e. the aromatic hydrocarbon, the methyl nitrite, and the NO. We carried out reactions to about 20 to 30% reaction, trying to keep it reasonably low. And the final one, and sort of the important one, is the final NO2 concentrations were estimated or calculated to be about 0.4 to 0.9 parts per million, sufficiently low that the OH-aromatic adducts were reacting mainly with O2 under our conditions. The aromatics were measured by GC-FID. We collected samples on 10x solid adsorbent, followed by thermal desorption, and then the analysis. The carbonyl products, these dicarbonyls, were measured by the solid phase microextraction fibers, or using fibers pre-coated with a derivatizing agent, and then subsequent thermal desorption and GCMS. These fibers, we pre-coat them with pentafluorobenzyl hydroxylamine, and then essentially put the fiber in the chamber for a certain amount of time. The carbonyls are derivatized on the fiber, and then the analysis is carried out. So this is, I keep losing this. There it is. So this is our pentafluorobenzyl hydroxylamine. They react with the carbonyl to give an oxime, and this can be readily gas chromatographed, whereas in many of the cases, for many of the compounds we're talking about, the carbonyl or dicarbonyl cannot be gas chromatographed without prior derivatization. And this is the fiber. Janet sort of showed, Potter showed the thing, but the fiber end is about 20 millimeters in length, and it can be retracted back into this metal tubing. We expose them to the chamber contents for about 5 minutes. It's surprisingly reproducible. We've used these for doing reaction kinetics and for quantification of reaction products. So look to be, depending on the person and the system, anything a few percent reproducibility. So we looked at all of these, well, 7 of these reaction systems. I'm only going to show one because once you've seen one, you've sort of seen them all. But we see diderivatized, these are the oximes, there's diderivatized glyoxal, mono, a little bit of mono, and mainly diderivatized methyl glyoxal in this particular case. And we see a a mono and diderivatized 3-hexene 2,5-dione. So the diderivatized is over here, and the mono is at the other side over here. We see the molecular weight 100 is in fact a second generation product from the 3-hexene 2,5-dione, and we also see some tolualdehyde, obviously para-tolualdehyde. And we've done this for all of the compounds, all of the aromatics. And what we get out of it are these. We see the various 1,2 dicarbonyls, so glyoxal, methyl glyoxal, and biacetyl. Janet seemed to have a better hang of this than I did. There it is. So we see biacetyl only from orthoxylene and 1,2,3 and 1,2,4 trimethylbenzene. As you expect, you're going to have 2 methyl substituent groups ortho to one another. So the 1,2 dicarbonyls is not a surprise. Those had all been seen by FTIR spectroscopy previously. Observation of many of these, or several of these unsaturated dicarbonyls is really the first time they've been, at least there's nothing in the literature on certain of them. The 3-hexene 2,5-dione, if I can figure out where I am again, this one here, can be gas, no, it's this one, can be gas chromatographed without derivatization, and we've seen that from paraxylene and 1,2,4-trimethylbenzene. But the pattern they form is in fact reasonably consistent with expectations. We don't see all of the possible unsaturated 1,4-dicarbonyls. There's a couple of them we don't see, and that's a sort of a point of interest. So this just says what I've already said. We see all the possible 1,2s, i.e. glyoxal, methyl glyoxal, and diacetyl. We see a series of the unsaturated 1,4-dicarbonyls. We see where we expect them, we see them pretty well. The one interesting one is that at low NO2 concentrations, the 3-hexene-2,5-dione, which we have previously quantified by GCFID and looked at, that from paraxylene, its yield is identical to the glyoxal yield as measured by Rainer Vokemer over the past few years. Clearly, the other interesting one would be to measure the yields of the 1,2-dicarbonyls, and if possible, these unsaturated 1,4-dicarbonyls, both get a quantification and also look at their yields as a function of NO2. Even for glyoxal and methyl glyoxal, the yields are for most of the aromatics are not really known under ambient conditions. They've been measured at part per million plus concentrations of NO2 and may not be applicable to ambient. So we really know those yields only for glyoxal from 1 or 2 compounds from the German group, and for biacetyl from a couple of 3 compounds from our own previous group or previous work. And this possible reaction scheme, this is what you can get by looking at the literature, largely from some German product studies carried out by German groups. And, geez, where is this thing? There it is. So you can form phenolic compounds. They're formed in maybe 10% yields. This is looking at toluene. This is potential reaction scheme for the OH-toluene O2 reaction. Form a certain amount of phenolic compounds. This is orthocresol in this particular case. The O2 is known to add to the aromatic ring to form a peroxy radical, but this is also known to be in equilibrium, and you get about as much of this as of the reactant species, i.e. the OH-aromatic adduct. And so these 2 species are roughly equivalent in the atmosphere. This is believed to undergo this cyclization and then react on further. And if you do that by a sort of rather hairy reaction scheme, you can end up with in this case, methyl glyoxal plus butene diol, i.e. the 1,2 dicarbonyls and their co-product, potential co-product, unsaturated 1,4-dicarbonyls. Well, we've shown that, this thing. Oh well. While we've shown that these 2 co-products are the same from paraxylene, excuse me, at least for glyoxal and 3-hexene-2,5-dione, the limited amount of data available doesn't suggest that that's not the case for many of the other 1,4-dicarbonyls. Their yields seem to be significantly lower than what their co-product 1,2-dicarbonyls are. And even if you assume that the 1,2-dicarbonyls and the unsaturated 1,4-dicarbonyls have equal yields, then on these products add up to about 60%. We're still missing some. And it's been thought that it may be these 1,6 diunsaturated dicarbonyls, but those appear to be only important at concentrations or NO concentrations in the part per million range, which is clearly not ambient. So there's still, and I'm sure anybody who saw Bill Carter's presentation a week or 2 ago on his mechanism would get roughly the same message, that the aromatics are not well understood. Okay, number 2, we started off, we wanted to quantify Glyoxal. We hadn't done it in the first task, but we wanted to continue on and be able to do that. You can buy Glyoxal, but you buy it as a hydrate, and getting it pure in the gas phase is a very tedious and not very easy job. And so we looked into getting a gas phase reaction to generate known amounts. Essentially do a gas phase reaction in one of our chambers and be able to calculate exactly how much, or well enough, how much Glyoxal would make. And looking around, looking at the reactions that produce Glyoxal, you like to have something with a carbon-carbon double bond in it that essentially gets cleaved across here. Glyoxal would then be this portion of it with an oxygen on it, and this compound looked like a potential candidate. So it's 3-methyl-2-butanol, and even better, you could buy it. So we went on and looked at that. So we measured this reaction rate constant. It's fairly reactive. We used the 7,000-liter chamber with GC analysis. We looked at the products by GC, mainly though by FTIR, using an in situ FTIR system in one of our chambers. And we also used the SPME, the Solid Phase MicroExtraction system, to identify and quantify one of the products, which is 2-hydroxy 2-methylpropanol, although its yield was only about 4 or 5%. So our evacuable chamber looks like this. This is from one end at the top and the other end at the bottom. And the system contains multiple reflection optical system inside. There's mirrors at this side, and on the other side you bounce the infrared beam to and fro, and the FTIR spectrometer is sitting here. So you get in situ data sort of as it happens. So there's sort of typical data that comes out. The top one is the initial compound, and then after reaction. And so top is our initial starting compound. The products are the second trace after subtracting off unreacted 3-methyl-2-butanol, and at the bottom we have some reference spectra for Glyoxal and acetone, and you can clearly see that there's acetone present, lining up with these, and acetone and Glyoxal. They overlap, but they can be easily subtracted or determined because one is quite structured, the other isn't. You take all those away and you're left with residual, which contains some absorption bands, which are due to organic nitrates, either peroxyacyl nitrates or organic nitrates. And so that's after subtraction. The formation yields, we have to make slight corrections, but it's quite accurately done, or can be accurately done, for secondary reaction of the products with OH radicals. And so this is just looking at acetone, Glyoxal, and our organic nitrates. We don't know the precise identity, at least not by the infrared, about 8%, 76% of the acetone. These are on the molar yield, and the one we're interested in is Glyoxal, so we get a 40% yield of Glyoxal. And so it's nice yield, high enough, certainly high enough to be used. The starting compound, 3-methyl-2-butanol, is significantly more reactive than Glyoxal, so that minimizes any secondary reactions. So it really is quite a nice in situ source, and we've used it quite consistently since, and I think it's been used by John Seinfeld's group at Caltech for some of their Glyoxal measurements. So then we used this to look at Glyoxal and other dicarbonyls from certain pAHs. We looked at Glyoxal from acenophthene and acenophthalein, Glyoxal and its potential co-product, aldehyde, and Janet mentioned these from naphthalene, and Glyoxal to acetyl benzaldehyde from 1-methyl-naphthalene, and Glyoxal and 1,2 benzene from 1,4-dimethylnaphthalene. The reason these were chosen was that we have authentic standards of the phthaldehyde, or you can purchase them, the 2-acetyl-benzaldehyde and the 1,2-diacetylbenzene. So these are our compounds as isonaphthene, isonaphthalene, and then these reactions, and I've drawn sort of the way the reactions appear to go to form these species. Janet mentioned these previously. So there's phthaldehyde, 2-acetyl-benzaldehyde, and 1,2-diacetylbenzene. And we want to see what the Glyoxal yields are, and are the Glyoxal yields the same as these aromatic dicarbonyls? So in other words, are they formed in the same yield and hence the same, presumably the same reaction pathway? Experiments again, Teflon chamber, OH radicals were generated by photolysis of methyl nitrite, or in certain cases, in the absence of NOx, by the dark reaction of ozone with 2-methyl-2-butene. A nice easy way of generating OH radicals. pHs were measured by GCFID, and Glyoxal by the coated SPME technique, and the aromatic dicarbonyl using an uncoated SPME. So this is Glyoxal from OH+naphthalene at various initial NOx or NO concentrations. These curves have all been displaced vertically for clarity. You notice one thing, or at least one thing I should point out, is that at the lower NOx levels, the amounts of reaction or extents of reaction become quite small. The initial naphthalene concentrations were also decreased, so you get fairly small amounts of reaction, and this does lead to some increased uncertainties. The other is that the amount of Glyoxal formed never exceeded 35 parts per billion, so this isn't exactly huge amounts, but certainly enough because the SPME technique is very sensitive to it. If we put all the data together as a yield, essentially this is the yield on the x-axis against the initial NOx, and I've plotted it as NOx. The average NO2 would be about 50% of that. And this is something we have to do as we're working this up for submission to a journal. But the Glyoxal yield seems to be about 6%, give or take a couple of percent, independent of the initial NO or NOx. So this suggests that there isn't any major difference as we change the NOx, and suggests that we've got one single reaction pathway, but that may not be the case. We looked at isonaphthene and isonaphthalene. We changed the initial NOx over the range of about 0.2 to 5 parts per million. We get about a 16% yield of Glyoxal from OH plus isonaphthene, and about about 1 and a bit percent from isonaphthalene. So there's a bit of a difference here. This, in fact, was to check on some earlier work we'd done several years ago, but never published, very preliminary work on these reactions. So we get essentially the same results as previously. But sort of maybe more interesting is the OH plus naphthalene, now looking at Glyoxal and phthaldehyde. The data are essentially indistinguishable. We get very similar yields of both. And if you plot phthaldehyde versus Glyoxal, a nice straight line with a slope of about 0.94. We've limited the data here to less than 30% reaction. Above that, on the major plot up here, the Glyoxal and phthaldehyde seem to increase more rapidly than one would expect by extrapolating this plot, suggesting that you're getting some secondary formation from the other dicarbonyl, which has all the carbons of the initial PAH, and we'd sort of anticipated that. But this is clearly primary Glyoxal and phthaldehyde, and our yields are about 4.9, or just about 5% of each. So they are relatively minor, and that agrees with the API-MS data that Janet presented a few minutes ago, where the major pathway seems to be breaking the ring at just one place and keeping all of the carbons. You still have a dicarbonyl, but it's retaining all the original carbons of the PAH. So we get reasonably similar data for 1-methyl-naphthalene and 1,4-dimethylnaphthalene. The Glyoxal yields about 4%. And while our measured yields of the 2-acetyl-benzaldehyde or 1,2-diacetylbenzene are a little higher, these are rather difficult or very difficult to calibrate the system. They need to be put into the chamber and then analyzed using the SPME technique. And there are certainly potential and almost certainly losses of these while either putting them into the chamber or to the chamber walls. Both of these co-products, 2-acetyl-benzaldehyde and 1,2-diacetylbenzene, decay to the chamber walls to a certain extent. So it's almost certain or more likely that these yields are in fact identical, or because if any losses will lead to a higher, an incorrect calibration and a higher yield. So Glyoxal is a product of all of these reactions, more so from isonaphthene than definitely from isonaphthaleine, where it's very minor. It's a relatively minor product from naphthalene and what look like the methyl and dimethyl-naphthalenes, at least the two we studied, and the corresponding aromatic dicarbonyl is formed in the same yield, suggesting that they're both formed in the same reaction pathways. The other thing is, and this will become evident in a moment, that or at least I hope it will, for the NOx concentrations used here, not the zero ones, but from anything above about 100 parts per billion of NO2, the dominant reactions of the OH-pH adducts are with NO2. And we've previously shown for naphthalene that the major ring cleavage product is 2-formyl cinnamonaldehyde, and the homologous dicarbonyls are formed from the other alkyl naphthalenes. So the final, but certainly not least, task was to look at nitro-aromatic formation from OH plus selected aromatics. And we chose toluene, naphthalene, and biphenyl. So as I stated in the beginning, under ambient conditions, aromatic or nitro-aromatic formation from monocyclics such as benzene, toluene, xylenes, trimethylbenzenes are going to be essentially zero under ambient conditions just because the NOx levels or NO2 levels are so low. OH, monocyclic aromatic, adduct is going almost totally with O2. However, the nitro pHs are observed in ambient, and that suggests or indicates that the OH-pH adducts are reacting with NO2 even under ambient conditions. And we have this mechanism, essentially the same as I've shown before, as I had before. So our OH, in this case naphthalene adduct, can react with O2 or NO2. And if the nitro-aromatic is formed in a yield of alpha, then the nitro-aromatic yield will be a function of the NO2. At very high NO2s, the yield will just be alpha. Essentially, every time this is formed, it goes this way, forms it with alpha. At low enough NO2s, then it will be just a linear function of NO2, because this will become insignificant compared to Kd times O2. And so, as I said, we looked at toluene, naphthalene, and biphenyl. Toluene, because there is some previous literature data extending down to maybe half a part per million. Naphthalene, because it's an interesting one, and it's clearly the simplest PAH. Biphenyl is not, depends how you define PAH, I guess. The nice thing about biphenyl is it seems to form a 3-nitro-biphenyl in fairly high yield. It's got almost exactly the same OH rate constant as toluene, and it seemed to be quite a nice one to look at. Naphthalene is about 3 or 4 times more reactive than toluene. Experiments were carried out again in one of these Teflon chambers. We used the same techniques for generating OH, either photolysis of methyl nitrite at greater than 0.1 part per million of NO2, and for less than 0.2 parts per million of NO2, we used the dark ozone plus 2-methyl-2-butene reaction. You can do that in the presence of NO2 up to a certain point. Above a certain NO2 concentration, ozone plus NO2 starts to get too important and makes NO3 radicals, and we saw some evidence for that, as you'll see. Analysis by GC and GCMS. A fairly complicated or complex series of analysis. Toluene and naphthalene were analyzed by GCFID after collection on 10x. Naphthalene and biphenyl by GCFID after exposure of dimethyl-siloxane SPME fiber, uncoated, to the chamber, and the nitros were analyzed by GCMS with negative chemical ionization after exposure of a SPME fiber, uncoated to the chamber contents. So there's 3 analyses done, 3 different systems. So this is 3-nitrotoluene from OH plus toluene. It's a log-log plot. So once you get below a certain point, you expect a linear, a slope of 1. Of course, a log-log plot has an attribute of hiding all sorts of errors in it. But still, we have what looks like quite a nice data set extending down to essentially ambient. This is about 20 parts per million of NO2. The range in the values down here is because we'd gone below or we're down to a level somewhat below what we could calibrate the SPME GCMS system for 3-nitrotoluene. You have to do it, form a calibration curve by putting the chemical into the chamber at the concentrations that you want to look for or look at. And these, in this case, we're getting down below 0.1 part per billion of 3-nitrotoluene. So we're starting to push the system down. The other is that the line here is exactly the same parameters as was used to fit our 1989 data, which went down to about 0.6 parts per million, which is somewhere down about here. So our previous data were all in this region here, actually about that region. So we've extended this down by essentially almost a couple of orders of magnitude, and really quite a nice fit with system. And you can see that the 3-nitrotoluene yield under ambient conditions is about roughly 10 to the minus 2%, which is close enough to be negligible. Okay, this is 1 and 2 nitronaphthalene formation, and we start to have some problem areas. One is this area in here, where we seem to have much higher nitronaphthalene formation than either higher or lower NO2 levels. And that's because both of our experimental systems are likely to be leading to NO3 radical formation. The methyl nitrite system, as you go down in methyl nitrite and NO, which you are forced to do to keep the NO2 down, you convert NO to NO2 more rapidly, or you get much more conversion because you've still got the naphthalene, the organic there. And once you get NO2, you then start to get ozone and hence NO3. And in the ozone plus 2-methyl-2-butene reaction, as you go up in NO2, the NO2 plus ozone reaction becomes more important, forming NO3. So we think this is due to enhanced nitronaphthalene formation from NO3 plus naphthalene, which has a yield something like a factor of 50 times higher than the OH reaction. If we focus on the data at the low end and at the high end, and these are quite reproducible, we did numerous experiments or a number of experiments on each set of conditions, then the OH-naphthalene adduct with O2 and NO2 were equal under atmospheric conditions at about 60 parts per billion of NO2. So this is starting to get down into ambient. And the yield, this curve is a yield, and it's really applicable for 2-nitronaphthalene of about 0.6%. So it doesn't make very much. And in fact, 1-nitronaphthalene seems to be a little lower at maybe 0.4%. These are consistent with what we've seen in the lab and published a couple of times previously, all around the roughly 1% sort of level, or slightly less. 3-nitrobiphenyl looks sort of similar. We again have this area, this section in here where we seem to have enhanced formation. It's exactly the same experiments, but NO3, there's no reports that NO3 reacts with biphenyl. We clearly need to, and we plan to look at NO3 plus biphenyl and see whether we do indeed form small amounts of 2-nitrobiphenyl. The adduct reactions, the OH biphenyl adduct with O2 and NO2 are now equal at about 600 ppb, intermediate between naphthalene and toluene. Much higher yield, much more like toluene, up around 12% from the OH biphenyl plus NO2 reaction. So the other thing we did was last year took some ambient samples in upland of toluene, biphenyl, naphthalene, and then nitro derivative or nitro products, and then try and see whether we can use those data to obtain yield data. So it's not simple, not surprisingly. So we've got these reactions. The OH plus the aromatic forms the nitro with a yield alpha. I didn't put that on, but the rate constant KOH. And nitro-aromatic can be lost by dilution. The atmosphere does have dispersion and dilution, or it can undergo photolysis. If you assume the steady state system, which isn't truly applicable, it may be for naphthalene, the naphthalene system, but almost certainly not for the others, you get this there we are. We get this reaction system here, which includes the OH concentration, which of course we certainly didn't measure, but we can get rid of that by referencing everything to 3-nitrotoluene over toluene. And we can get that if we know the ambient NO2 concentration, which we get from South Coast Air Quality Management District, at least reasonably okay. We can get this value from our chamber dip, from our lab experiments, and then try and determine what this would be for naphthalene or biphenyl. And we need these numbers. We have the photolysis rate constants for 1 and 2-nitronaphthalene. That's been measured by Patricia Poon-Sung Kwang and Janet a few years ago. We have the OH rate constants. We have to make an estimate of dilution. We had some data back in 1986 in Glendora, which allowed us to sort of extract an atmospheric dilution number. But luckily, or at least fortuitously, well, luckily, I guess, neither 3-nitrobiphenyl nor 3-nitrotoluene appear to undergo photolysis, at least not at any significant rate. So for those systems, these just drop down to alpha times KOH, because the bottoms all drop out. The KD, the dilution's the same in both systems, and no photolysis. KOHs are very similar for biphenyl and toluene, so we're left looking at, essentially, we get the ratio of the formation yields from the OH system, or from the reaction system. So if we do that for naphthalene, we get fairly consistent data with consistency between our ambient and lab data for 2-nitronaphthalene, but the 1-nitronaphthalene is significantly higher. Not just that's certainly expected, because 1-nitronaphthalene photolyzes much more rapidly than 2-nitronaphthalene, and yet they're present at the same concentration in ambient, and they're formed in the lab at essentially the same formation yield. We still, I just note this is our lab data. The open circles are lab data, and the colored ones are derived from ambient. And this suggests, as we had sort of been expecting, that there's something going on with 1-nitronaphthalene. Is it a direct emission? It is the electrophilic nitration product, so it could have other sources or sources other than atmospheric formation. 3-nitrobiphenyl, our lab data is the open circles. Again, I've indicated this with the red triangle with this area where we seem to have some artifactual formation, presumably maybe from NO3. But the ambient data down here, or the yields derived from ambient data, are quite consistent, or reasonably consistent with our lab data. So we can now come to the sort of the bottom line is that the 3-nitrotoluene formation yield dependence on NO2 is well known, or at least seems to be totally, or is totally consistent with literature kinetic and mechanistic data. And the OH-toluene adducts react with O2 under atmospheric conditions, or nearly totally, not quite totally, but mostly with NO2. OH-biphenyl adducts react with NO2 down to about 600 parts per billion of NO2, and OH+naphthalene down to about 60. So this is starting, this explains why we do see OH, or at least nitrobiphenyl, and nitrotoluenes, and presumably the other nitro-PAHs during daytime in the ambient atmosphere, and the lab data are generally consistent with ambient measurements. So we do have a nice sort of rounding it around and consistency of things. And the people who carried this out, Noriko Nishino, who did the Glyoxal from the OH-PAHs and all this Nitro-aromatic work. She's a present PhD student between Janet and I. Roland Kusek, who was an undergraduate at UCR, who worked on the dicarbonyls from the OH monocyclics, and Salika, who is currently an ARB employee down in, or Dr. Salika Chalapadny, who's currently at ARB in El Monte, who was a postdoc with us, doing the dicarbonyls from the monocyclic aromatics. Okay, thank you.